So, you're building an aircraft and need to use the input system. Today we will be covering how the input system works, as well as some practical examples such as Canard settings, landing gear doors, and more. As usual, the video is broken into chapters with timestamps on the screen now. Parts that can respond to the input system have this blue section in their settings pane. If there are multiple aspects of the part that can respond to an input, there will be additional input sections alternating between the first blue color and a greenish color. Starting at the top of the input section, we have copy and paste buttons. As their names suggest, these are used to copy settings from one part to another without having to retype everything. To the right of these, there is the Set Mirror button, which is used to copy the input settings on the selected part to the part mirrored to it, if it was placed with symmetry enabled. This should be used anytime you want to copy settings over to a mirrored part, as it will correctly set asymmetric inputs such as roll to the opposite sign. Note that mirrored parts do not automatically inherit input settings from one another, so you should use the Set Mirror button anytime you make changes and want them to reflect on the other part. Next we have the response speed field. This is the maximum rate at which a settings output can respond to its inputs. With a control surface, for example, the value here is how many degrees the surface will deflect over 1 second. Next is the default value field. This is the value that the output will start at when the inputs are at 0. The range field describes the minimum and maximum values the output can reach. The lower number must be on the left and the maximum must be on the right. If both values are the same, the output will simply stay at that value. Finally, we have the responses field. Here you can select one or multiple inputs for the part to respond to. The input system uses a simple equation to calculate the output value based on any inputs and the default value. Simply put, the output value is equal to the sum of each response value times the respective input value itself plus the default value. Here's an example of this equation being used with just one input and no default value. Suppose I have an input whose range is from -1 to +1. If the part's response is 10, the output value will range from -10 to +10, assuming the range fields allow that. If a default value of +5 is added in, the output will range from -5 to +15. However, the maximum value is outside the output's maximum range value, and the output maximum will be capped at +10. Before we move on to the next section, note that all of your inputs can be viewed in flight by pressing F4. This is a great way to determine input ranges if you aren't already familiar with them. Custom inputs will show up at the very bottom of this list. I will describe each stock input at the end of the video. The input system can also be used with user-defined inputs of 3 different types: switch, step, and slider. To create a custom input, click the gray gear icon in the upper left and then go to Inputs. All custom inputs have the basic input fields, minimum and maximum values, a default position, and sensitivity. The min and max values are self-explanatory. The default position determines what value the input will have on startup. The sensitivity value affects how quickly an input transitions between its minimum and maximum values. 1 unit of sensitivity means that it will take 1 second for an input value to change by 1. For example, a switch with a minimum value of 0 and a maximum value of 10 with a sensitivity of 1 will take 10 seconds to transition between states. Custom inputs can also be assigned keybinds to increase their value, decrease their value, or toggle between min and max values. When you're done editing your input, be sure to click the return button at the top of the menu to save your changes. The first custom input type we will look at is the switch. A switch has 2 states, on and off. When the switch is on, its output will be the maximum value. When it is off, its output will be its minimum value. The default step can either be 0 or 1, corresponding to whether the switch starts at the off position or the on position, respectively. As an example of how to use the switch, I will have a swing joint respond to it. In the response dropdown, I scroll all the way to the end and pick the switch input. In this example, I want the joint to rotate from -90 to +90 degrees. Because the switch input has a range of -1 to +1, my response value will be +90. Once the craft is loaded in, note that the hinge does not remain at 0 degrees. Although the joint's default value is 0, the minimum value of the switch is telling it to go to -90 degrees. When I change the switch to its max value, the joint takes a much longer time to travel than the input does. This is because the joints have their own separate travel speed, which can be changed in its settings. If I lower the switch's sensitivity to where it is slower than the joint will move slower than its own speed setting. Going back to the editor, you may have noticed the graphical overlay the joint shows when it is selected. The display shows the range, starting position, and default value of the joint. The blue area shows the range over which the joint will rotate. If I have a default value, it will be displayed by a red line. The green line shows where the joint starts on startup. It is important to remember that the default value is simply an offset in a part's output equation and does not always represent where an output may be at its resting position, depending on the resting values of the inputs and the responses to said inputs. For example, let's say I want to cap the lower limit of the joint to -45 and mistakenly set the default value to -45 as well. Recalling the output equation, if we plug the switch input's minimum value and the default value in, the input with the switch off is -1 times 90 minus 45, which is equal to -135. Because the joint's range is capped to -45, it won't go past that, which works fine for my intentions, but let's take a look at what happens when I turn the switch on. As the switch changes value, the joint remains stationary until the switch's value reaches 0, as this is when the overall output equation yields a value of -45. When the switch is at its maximum of 1, the joint stops earlier than the intended 90 degrees. Recalling the output equation, plugging in the switch's maximum value, we get +1 times 90 minus 45, which is +45 instead of the desired 90. Another point to be wary of is the mass of the joint you use. If a joint's mass is too low, it can become too weak to support whatever is attached to it, and something related to the joint's physics will cause the game to either go to a black screen or crash. Thus, it is important to set your joint's mass multiplier appropriately. How heavy a joint needs to be to work depends on the mass of whatever is attached to it, so heavier objects need a heavier joint. A very safe ballpark value to start at is 15 kilograms and then work from there. If you need to go outside of the mass multiplier's in-game limits, you can edit the mass multiplier in the craft file. Just name the joint something you can recognize, open the craft file in a text editor, and search for the joint name, then change the mass multiplier's value. Next we have the step input. The step input changes its value by a fixed increment each time you increase or decrease it. Unlike the switch input, it cannot be toggled. The amount it increments by is equal to the quantity of the maximum value minus the minimum value divided by the number of steps. The number of steps is unfortunately not so straightforward to set, however. Instead of being able to pick an arbitrary number, the number of steps must be equal to the maximum value of the input unless you change the maximum value after the number of steps has been set. I'm assuming this is a bug, so maybe we'll see this change in a future update. With that said, you will need to calculate the response value you need accordingly. Going back to the rotating joint, I will need an input response of 30 with the input's maximum value of 3 to reach +90 degrees. Each increment will change the input value by 1, which yields a rotation of 30 degrees per increment. Using the step input, I will demonstrate another use of a part's default value. Suppose I want a light to stay off until a certain input value is reached. To do this, I can use the default value to keep the overall output below 0 until it needs to change. I will use this to make the second and third lights only turn on when the step input reaches the second and third increments, respectively. Note that an output value of 1 corresponds to a light being fully lit. With this in mind, I can leave the response value at 1 so the first increment turns on the first light. The second and third lights will both turn on if I don't change the default values. For the second light, I want it to turn on when the input is at its second step, which has a value of 2. Because I want the overall output value to be equal to 1 here, the default value is calculated to be -1. This will ensure the output's value stays at or below 0 until the second step is reached. The third light's default value is calculated with the same process, but with an input value of 3 instead of 2. Solving for the default value, we get -2. This process is useful for any input type, and is especially useful for making lights or meters in your aircraft, such as these flat position lights. Finally, we have the slider input type. The slider is similar to the step input, except it can be set to any value along its range instead of changing at a fixed increment. Unlike the other two input types, it also has the gravity field. A non-zero gravity value will return the slider to its default value when the increase or decrease value keys are not being held. Similarly to sensitivity, the magnitude of the value in the gravity field determines how quickly the slider returns to its default value. Also similarly to sensitivity, the value in here is speed in units per second at which the slider will return to the default value. Now that I have covered the basics of the input system, I will go over some practical examples of how to put the input system to use. The first example will be for landing gear doors. To make gear doors, simply attach an appropriately shaped fuselage to a hinge. Make sure that the door itself is also outlined in yellow when the hinge is selected so you know it's properly attached. For this gear door, I would like it to stay open while the gear is deployed and close when the gear is retracted. At first, this may seem as simple as adding a landing gear response to the hinge. However, we quickly run into the issue of the door not waiting for the gear to retract before closing, and the gear not waiting for the doors to open before deploying. To force the doors to wait to close, we will need a slider input with a sensitivity high enough to instantly jump to its max value when the increased value key is pressed. We will bind the increased value key to the landing gear key, which is G by default. The gravity value will also be needed to return the slider to 0. The purpose of this slider is to act as a delay by keeping the door hinge's total output at its deployed value of positive 90 degrees. When G is pressed, the slider will snap to its maximum value and will slowly decrease back to 0, all while staying out of the range of the hinge's output value. As we can see, the delay works, but we still need to address the gear deploying before the doors are open. For this, we will need another delay slider with similar settings to the one used for the doors. You could technically use the same slider twice, but having two allows for better customization of the settings to suit your needs. Keep in mind that the gear's output value range is only 0 to 1, so our delay response can stay a single-digit value for our needs. For a more focused tutorial on landing gear doors, I recommend checking out Angel of Death's sequenced landing gear door video linked in the description. Suppose I would like my wings to automatically sweep beginning at a designated start speed and end at a designated end speed. For this example, I will have the wings start sweeping at Mach 0.6 and end at Mach 1.0. To calculate the required default value and response value for this to work, I need to set up a system of two equations with the outputs being the desired sweep angles at each speed. For the first equation, I want the sweep angle to be 0 and the Mach input to be 0.6. The default value and Mach response remain unknown. The second equation has the sweep angle at 48 degrees and the Mach input at 1.0. Now that we have two equations with two unknowns, we can solve the system of equations for the Mach response and default value by doing a simple substitution. This method works for any situation in which you need an output to only work between two input values. I've set up a Desmos calculator that can be used to solve for the response and default values required to get a certain response within a certain range using the same method. You can find the link to it in the description. For this example, we will look at decent response settings to give a Canard for a combat aircraft. This will require applying multiple inputs to one part. The first and most obvious input to apply is pitch, as I want the Canard to contribute to my pitch control. The response is negative so that the leading edge will deflect upwards when I pitch up. Although this Canard will indeed contribute to my pitch control, I need to be wary of the angle of attack it will reach in flight. If it pitches up too much, it will stall and won't contribute any meaningful lift while I am turning. This is why I have the maximum angle at positive 10 degrees. Another condition to consider is the deflection of the Canard when the aircraft is at a relatively high angle of attack. If the aircraft is at a high angle of attack and the Canards are deflected upwards too much, this will create another condition for them to stall due to the total angle of attack they experience. To prevent this, I will add an alpha response, where alpha is the Greek letter used to symbolize the angle of attack. In the input system, alpha represents the aircraft's angle of attack. This response will begin deflecting the Canard downward slightly even when I'm pitching up. This way, it will maintain a positive angle of attack that isn't past its stall angle during maneuvers, and will continuously generate significant lift when I need it to. You can also add a roll response if you want the Canards to contribute to your roll control, although you will still need to make sure they won't stall when rolling at high angles of attack. A steep brake response can also be used so the Canards act as air brakes after you land and enable the brakes. The final example I will cover will demonstrate how to achieve linear actuation with the current joints in Flyout while making a visually functional shot cone intake. Currently, Flyout does not have any linear actuator parts, so we will need to make do. In this case, I will be using swing joints. I recommend placing a fuselage piece before each subsequent joint, as attaching joints directly to one another can cause some physics issues due to quirks of NVIDIA's PhysX system. The distance the actuator extends will depend on the distance of each joint connection, which should both be equal, as well as the angle that the joints will rotate. A larger angle of rotation will facilitate a larger extension. In my case, I need the outer joints to rotate 60 degrees to reach their maximum extension. The joint in the middle will need to have double the range of rotation and rotational speed to keep the extension in a straight line. When we add responses, those will need to be doubled here too. Speaking of responses, I want my intake to extend beginning at Mach 1 and ending at Mach 3. The required responses and default values are calculated using the same system of equations method from earlier and are visible on the screen. Finally, I will be listing all of the stock inputs. Starting from the top, we have pitch, roll, and yaw, all of which have ranges from -1 to +1. Roll and yaw, left and right, correspond to inputs of -1 and +1, respectively, whereas pitch up and down correspond to -1 and +1, respectively. The flaps input ranges from 0 to 1 in increments of 0.25, with 0 being retracted and 1 being extended. The brake input ranges from 0 to 1, with 1 being engaged and 0 being disengaged. The throttle input ranges from 0 to 1, with 1 being full throttle and 0 being idle. Collective ranges from -1 to +1 and has the intended use of adjusting the blade pitch of helicopter blades. It is adjusted with the 3 and 4 keys. The landing gear input ranges from 0 to 1, with 0 being extended and 1 being retracted. The lights input ranges from 0 to 1, with 1 being on and 0 being off. Time counts upwards in seconds starting from 0 and reflects the amount of real time passed since the aircraft was launched. It does not reflect the local time on the planet. The Mach input simply reflects the aircraft's current Mach number. ASL is the aircraft's altitude above sea level in meters, and AGL is the aircraft's altitude above the terrain beneath it. If you are above a body of water, this will track the terrain underwater instead of the water's surface. Alpha is the angle of attack in degrees of the aircraft's centerline relative to the longitudinal component of the incoming free stream airflow, with positive indicating the incoming air is below the plane's centerline and negative indicating the air is incoming from above the plane's centerline. Slip is the side slip angle in degrees between the aircraft's centerline and lateral velocity component of the incoming free stream airflow. In Flyout's case, positive slip indicates air incoming from the left and negative indicates air incoming from the right. Those of you watching who are versed in aircraft flight dynamics and controls may have noticed that this is the opposite to the common convention of a positive slip angle coming from the right instead. As we get to some of the later inputs, you may soon realize that Flyout does not use the conventional aircraft body frame with positive X, Y, and Z corresponding to the nose, starboard, and down directions, but instead has a positive X, Y, and Z corresponding to the starboard, up, and nose directions, respectively. This also does not follow the right-hand rule. Pitch attitude is the pitch angle of the aircraft relative to the local horizon. The bank input is simply the bank angle of the aircraft, which is the roll angle of the aircraft relative to the local horizon. Positive reflects a left-hand bank, and negative reflects a right-hand bank. Heading is the direction of the aircraft pointing relative to true north, which increases in the clockwise direction. Course is similar to heading, except it represents the direction the aircraft is actually moving instead of where the nose is pointing. Currently, this input is bugged and has a gap between 60 and 120 degrees and 240 and 300 degrees. Climb is the climb rate of the aircraft in meters per second. G is the ratio of the aircraft's body-centric vertical acceleration to the gravitational acceleration of the planet at sea level, which is 9.81 meters per second. In other words, it's just how many G's you're pulling. Static pressure is the air pressure of the local atmosphere measured in pascals, or newtons per square meter. Dynamic pressure is a quantity used in aerodynamic calculations and is equal to 1/2 of the local air density times the square of the free stream velocity the aircraft is experiencing. Below Mach 0.3, where compressibility of air is negligible, dynamic pressure also has the special property of being the difference between stagnation pressure, which can be found in the conditions window, and static pressure. Static temperature is the temperature of the local atmosphere measured in Kelvin. The X, Y, and Z accelerations are the linear accelerations the aircraft experiences on each of its 3 body axes in meters per second squared. The X, Y, and Z angular velocities are supposed to be the rotational rate of the aircraft about each axis in degrees per second, with X being pitch rate, Y being yaw rate, and Z being roll rate. However, it appears these values are actually swapped with the angular acceleration values, which are the rotational acceleration rates about each axis, in radians per second squared. As their names imply, airspeed X, Y, and Z represent the aircraft's airspeed along with each of its 3 axes. Velocity X, Y, and Z represent the aircraft's ground speed along each axis.